This tutorial will introduce you to the basics of mesh geometry in comparison to NURBS geometry that you've already learnt about. I'll show you some simple ways to construct meshes from scratch, that is from lists of points that become vertices in the mesh. I'll also quickly demonstrate a practical reason for using meshes in Grasshopper, and I'll show you some existing tools from the mesh tool panel to play with some form that we might not be able to model using NURBS. So to begin with, let's have a look at the mesh menu. Grasshopper comes with a bunch of components for analyzing meshes, things like breaking them down into individual faces or triangulating meshes, finding edges, calculating areas, things like that. We also have some components for constructing meshes from scratch, which is this one here, and for creating mesh primitives. There's a few components which you guys might already be familiar with for using various meshing algorithms to create new geometry or to partition space in the case of the octree component, and there's some utilities for modifying meshes in various ways. So for now, let's construct a mesh from scratch using this mesh component. You can see from the inputs it takes three different parameters to get started. We need a list of vertices, we need a list of faces, and we can optionally have some colors for those individual vertices. I've already created some points in Rhino here, and to demonstrate just practically how these mesh objects work, I'm just going to create two simple mesh faces here to form one single mesh. Now, it's rare that you'd ever do this in Grasshopper as a modeling tool, but it is nice and simple to demonstrate how these things work. So let's create a point parameter and reference in these points. And for the purposes of demonstration, let's also use one of these point list components to display the order that these points are stored in this component. So this is point 0, point 1, point 2, point 3, point 4, point 5. I'm just going to turn off these lines, they're annoying. Now they're going to be the vertices for our mesh, so we can plug them straight in, and now we need to create the faces. So a face object, up here in our primitive panel, mesh quad, we're going to create four-sided faces. A face object is not geometry in itself. All it's doing is telling this mesh component how to join these vertices together in order to draw a face. So all it's doing is asking for four different indexes of the points in this vertex list. So if we wanted to create a face between these 4 points here, we'd tell Grasshopper to create a quad face, and then say for the first vertex, point 0, for the second vertex, point 1, for the third vertex, point 4, and for the fourth vertex, point 3, which is what these 4 inputs are saying here. And now by default, if we connect this up, it's connecting point 0 to point 1 to point 3 to point 2. So if we want to change the vertices that this is using, so we want 0, 1, 4, 3, we can keep 0, we can keep 1, let's change this one to 4, and let's change this one to 3. And then we have our face. And you can just keep doing this, and again, this is why it's a little bit impractical and you'd rarely do this in practice, for any other faces that you want to make. So we can have point 1 to point 2 to point 5 to point 4. And there you have it, you're starting to construct a mesh entirely from scratch. Now, as I mentioned before, this isn't something that you would practically want to do because you'd need to keep copy-pasting these quads to articulate how the faces fit through a humongous list of vertexes. So if you had a mesh with thousands of vertices, which isn't uncommon, you might need thousands of these quad components, which is just not very practical at all. So the way we can get around that sometimes with Grasshopper is to organize our points into a data tree, which will come later on in other tutorials. Now I'm going to quickly show you an example which is included in this week's Grasshopper file, just to demonstrate how we might practically use this mesh from scratch component. So in this case I'm piping, or at least approximating a pipe along some curves using a bunch of quad mesh faces. I can only do this using a data tree, otherwise, as I mentioned before, we need lots and lots and lots of these quad components, and it lets us create an approximation of all of these curves. Now the reason we might do this rather than using a NURBS pipe component is simply because NURBS pipes take a really long time to calculate, whereas meshes are simply drawing quad faces. It's optimized for your graphics card and everything runs really smoothly. So if things don't need to be too accurate, or if you're planning on 3D printing something, you can just stick with using meshes. Okay, back to the tutorial. Now another practical example of using meshes in Grasshopper is to perform some modeling operations that you couldn't necessarily perform using just NURBS surfaces. So to do this, we might take a model which we'd already modeled using NURBS, such as this polysurface here, reference it into Grasshopper using a BREP component, now BREP just stands for boundary representation, and it says in brackets here polysurface, and we can convert it to a mesh using this mesh BREP component. So we plug in our BREP, can hide this preview, you can even hide this geometry, and it takes that geometry and it just triangulates all of the faces. So what used to be NURBS surfaces is now a whole set of vertices and these face objects. And by default it tries to create as few as possible, but we also have settings for changing how it meshes the object. So let's look at this custom settings component. Lots and lots of inputs, and these control how many faces are used to approximate this NURBS surface. Now, as I mentioned before, NURBS surfaces are continuous and smooth because they're interpolated between NURBS curves, which are themselves interpolations between control points. So no matter how far you zoom in on one of these surfaces, it's always going to be infinitely curvy. Now if you look at this little mesh that I made, it's not curvy at all. It's composed entirely of straight edges. So that's what makes NURBS discrete geometry. Everything is explicitly and discretely specified using these coordinates of vertices. So while I meshed an already fairly rectilinear geometry over here, if we mesh this surface, you'll see that it's really only approximating that surface geometry using all of these mesh faces. And basically what this component does is it's quite clever. Where the surface is more curvy, it makes smaller faces, it triangulates them more, so that there's minimal distance from the new mesh vertices to the surface all the time. So it can, as closely as possible, approximate this surface. Anyway, back to our other geometry so I can show you the trick. So now that we have this mesh, we can start playing with the mesh object in ways that we couldn't with the NURBS object, using some of these utilities here. So I'm going to weld all of the vertices to begin with, which just means that any coincident vertices, in other words 2 vertexes in exactly the same spot, become one single vertex, and that means faces start sharing edges. So the whole mesh becomes continuous topologically. Everything is connected to everything else. Hide the component. Once everything's connected, some of these components start working like smooth mesh. And what smooth mesh does is it smooths or it averages the vertices of this mesh object. Now I'm just going to add some iterations, and you'll see the more we run that algorithm, the more relaxed or the more smooth that mesh geometry becomes. And I've just chosen this strange shape because it's kind of like 2 toruses connected together, which would be extremely difficult if you were modeling it only using NURBS surfaces. I've also chosen this geometry just because it shows how you can go from something quite boxy to something fairly organic using these algorithms. Otherwise it's completely arbitrary. So this tutorial has introduced you to some of the basic principles of mesh geometry. It hasn't gone into all of the components in the toolbar, and I suggest that you go and check some of these out when you have time. Joining meshes can be really useful, splitting meshes can be useful. Some of these components for testing occlusion and exposure are kind of interesting. All of the triangulation components are really easy to use and interesting and are great for playing around with spatial partitioning stuff. The analysis components do all sorts of useful things as well, especially stuff like extracting face boundaries, because this will let you take your mesh geometry, which is fairly difficult to continue working with in Grasshopper, and convert it back into a set of polylines, so that you can start using any of these components in the curve menu to continue working with the object. If you really want a challenge, try modeling 2 toruses connected together with a single surface. See how you go.